Hello everyone, I'm very honored to participate in this conference. I'm very happy to have the opportunity to introduce our paper, protein2vec, which can predict protein interactions based on LSTM. Here is the outline. I will introduce our paper from these 6 parts. Firstly, the introduction includes 3 parts: the background of PPI, related work, and the motivation of our method. Prediction of the PPIs is widely used in drug delivery control, function prediction, and etc. In order to identify new interactions, some small-scale experimental methods have been proposed, but they are expensive and time-consuming. Therefore, many researchers have proposed computational methods to predict novel PPIs, which can guide experiments. We roughly classify the computational methods into 5 categories, which is shown in this slide. Among these computational methods, the semantic similarity measures based on the goal are widely used. The proteins annotated with the same or related goal terms may have similar cellular location and biological processes. Therefore, the prediction of PPI can be inferred from the similarity between goal terms. These different methods shown in this slide use different rules to define the similarity between goal terms. These rules are generally based on the common ancestors, passes, and other elements of the goal. Methods based on machine learning or NLP only use the information of the goal, and the method based on PPI network only uses the information of PPI networks. In summary, the traditional semantic similarity methods suffer from 2 limitations. Firstly, the feature selection is based on personal observations or intuitions, which may ignore some important hidden information of the goal. Secondly, they usually obtain the similarities between proteins from similarities between goal terms by some simple statistical rules, such as max or BMA. To alleviate the deficiency of the existing semantic similarity measures, we propose a new method named protein2vec, which characterizes a protein with a vector based on the terms and combines the information of both the goal and the known PPIs. And secondly, I introduce the method from these 3 parts. This figure shows the framework of protein2vec. In the left is the term encoding module. It uses Node2vec to transfer all goal terms into their corresponding low-dimensional feature vectors. In the middle is a protein encoding module. The input to this module are 2 sequences of feature vectors, such as SA and SB, which correspond to proteins A and B. These 2 sequences are encoded by 2 parameter-shared LSTMs, respectively. The output of the module is 2 protein vectors, PA and PB. In the right, it's a prediction module. It's a feed-forward neural network. It takes the 2 protein vectors, PA and PB, as input to predict the presence or absence of interaction between the 2 proteins. That is output of probability distribution. In this slide, we show the network architecture of the term encoding module. It consists of 3 layers. In the input layer, goal terms expressed as one-hot encoded vectors with dimension n are input. The output layer has several identical channels. Each neuron in each channel corresponds to a specific goal terms. In the hidden layer, it has key neurons. Each neuron corresponds to an extracted feature. By training the network, we get the feature vector for goal terms from the well-trained metric between the input layer and the hidden layer. The protein encoding module is an encoded model based on LSTM that learns the mapping relation from terms to proteins. It consists of 2 identical LSTMs. This figure shows the details of the 1LSTM. If it's fed with a sequence of the feature vectors of the protein, the LSTM network outputs a sequence of the hidden state. The final hidden state vector HT is taken as the protein vector for the protein. Our experiments involve these datasets. The file of Go and gene annotations were downloaded from the Go database. Their version is shown in this slide. We used 3 PPI datasets, equally as Cerevisia and Homespace, to compare protein2vec with other semantic similarity approaches. The distribution of the PPI interactions of these 3 datasets are shown in Table 1. We adopted the same sequence homology dataset provided by SAMDEF, and we adopted the gene expression dataset provided by CCSS. Next, I introduce the experiment from these 3 parts. We divide the dataset in 2 models, division with connectivity and division with five-fold cross-validation. We use equally connectivity and equally five-fold to evaluate the ability of protein2vec and other approaches. The experimental results are shown in Table 2 and Table 3. Protein2vec is significantly better than other semantic similarity methods on those 2 datasets in the AUC scores. We test all 6 methods on the Cerevisia datasets. It's clear that protein2vec gives the best performance on both these datasets for CCBP and MF ontologies. We performed a similar experiment on the home-switch PPI dataset. According to the Table 6 and Table 7, protein2vec achieved competitive performance. We used the correlation with sequence similarity to test the performance of protein2vec and other methods. Our RBS and RBS scores in the sequence homology data reflect the sequence similarity. Figure 5 shows the PPC between protein similarity and RRBS, and Figure 6 shows the PPC between protein similarity and RRBS. The prediction result of our model is better than other semantic methods except SAMDEF, which indicates that our model have a good performance in inferring the PPI. We use the gene expression data to evaluate the semantic similarity. Table 8 shows the PPC between gene expression data and the semantic similarity scores from protein2vec and other methods. As seen in Table 8, the performance of CSS is generally best, and our protein2vec model performs slightly less than it. Finally, we make some conclusion. In this study, we propose a new method, protein2vec. Our method achieves good performance on equally and as Cerevisia datasets compared with other semantic similarity methods. We also evaluate the generalization ability of our method in both the sequence homology dataset and the gene expression dataset. It can be concluded that our method is a comparable measure compared with other semantic similarity measures. That's all for my presentation. Thank you for your listening.